Well, good morning. Today we will approach randomized controlled trials. How do you critically appraise a randomized controlled trial that has been subjected for a protocol or a research paper? And I will also teach you how to get random allocation sheet from the Excel. Here we are telling you why there should be a random selection over the sufficient sample size for your study population to be representative of the source and the target population. Source is the source of the study population, and it's expected that the target population will come from the source only. So this big square is the truth. It is the whole population. And this you are not studying. You have to take a sample from it. So if the whole population was divided artificially into exposed and affected, exposed and not affected, not exposed and affected, and not exposed and not affected, the A, B, C, D numbers, then you must choose this square where the A, B, C, D, small a, B, C, D have an equal probability of getting selected from A, capital B, capital C, and capital D. Now, the random selection over a sufficient sample size would get you small a representative of big A, small b representative of big B, small c representative of big C, and small d representative of big D. And all these numbers, A upon A, B upon B, C upon C, D upon D, will be equal to sample size total upon the total population of that problem, that particular problem. So this equal probability of selection of all units in the source or target population is achieved by random selection over sufficient sample size. So the first thing that you have to understand is that your population, if you have selected wrong, for example, you made this square, this one, which is not in the center, then there will be a much greater probability of selection of A. And therefore, the relative risk, odds ratio, and risk difference that you get will be much more association than is actually true in the target population. So this is called a selection bias. The second thing is that instead of measuring here, supposing you measure here, then the A will become smaller and B will become larger. And therefore this square, not only the outline, but also the measurement can differ from the actually true measurement. So selection bias is that the outline is wrong, and the measurement bias is that the measurement between affected, not affected, and exposed, not exposed does not correspond to the truth or the valid measurement. So there are two types of bias, selection bias and measurement bias. Issue is that any protocol or study should avoid these, and you as a reviewer of the protocol or the paper must be able to suggest whether there is any random bias, random selection error, that means selection bias, outline bias, or measurement bias. This is what you should look for in the methodology. Now, random selection is different than random allocation. Random allocation is to two treatment groups, and when done over a sufficient sample size, it would render all the groups, all the treatment groups equal on all other explanations of results, which means known and unknown confounders, so that the only explanation of the difference that you see at the end of the study is because of the difference in the treatment time. Now we teach you how to critically appraise a randomized control trial. This blue is the source population from which the target population will come, and therefore the results of your study population will become generalizable or externally valid on the target population. So these, if you divide it into the 2 by 2 table, exposed good results, exposed not good results, unexposed good results, unexposed not good results, these big A, B, C and D, then if your sample population has been randomly selected over sufficient sample size, then A will be representative of capital A, B to capital B, C for capital C and D for capital D. So if this situation doesn't exist, then there is a selection bias, because random selection over a sufficient sample size is the only way to give all units of this blue population equal size, equal probability of being selected in the study population. So after this, if you randomly allocate to treatment A and treatment B, then this random allocation will render this group and this group equal on all other factors which can explain the results except the treatment type. Therefore, this will take care of confounding. So this is random allocation, and it's the best way to control known and unknown confounding. And it is tested by comparing both the groups, this group and this group, on all other factors of which you have the data. And if they are none of the p-values is significant, then your random allocation is successful. Otherwise, for that factor where the p-value is not significant, you may have to use regression analysis. So then the treatment group itself. Are the treatment groups sufficiently well described to be accurately reproduced in other settings? That's the question you ask. Then about the follow-up. So, is the follow-up sufficient for all relevant outcomes to occur? That means the duration. The second question is, has he dealt with loss to follow-up? Those that have been lost to follow-up. In this, supposing your results are saying that treatment 1 is better. So what you'll do, you'll ascribe the loss to follow-up as treatment outcome worst. That means you are going to reverse the results that you are getting. And in this group, you are going to reverse the results that you are getting for this treatment group. So that your hypothesis is reversed if you assume that the loss to follow-up did not have the same outcome as the people who have been followed up. So this is called as the worst scenario approach, and that's how you deal with the loss to follow-up. And if your difference in results, so the direction of results survives this maneuver, then the loss to follow-up is not fatal. It is not a fatal mistake. So this is about loss to follow-up. Then about somebody may have taken a co-intervention, that means some other type of drug which may affect the results, or there may have been a friend in treatment group 1 of treatment group 2, and this fellow may have been told that I am much better, so he may have switched over to this treatment group 1. This is called as contamination. So in follow-up, you have to deal with loss to follow-up, contamination and co-intervention. Then if you are measuring the outcomes, so first of all, question is, have all relevant outcomes been measured? Has the measurement been precise and valid, which means no false positive, no false negative? Has the measurement included cost, effectiveness, risks and outreach, that means the ability to apply it to the general population? Has the measurement been done at sufficient frequency for a sufficient duration? And has the outcome measurement in treatment group 1 measured at the same time as in treatment group 2. So these are the questions that you have to ask about when the measurement or when the outcome was measured. The second thing is that there are two ways to measure outcome. One is subjective, the other is objective. The subjective outcome is measured by an observer, and if the patient and the observer do not know which treatment group they belong to and what is the research hypothesis, then subjective outcomes are measured precisely and validly. Otherwise, there is a measurement bias which is introduced because the subjective component has a biased observer or a biased patient. Patient, to please you, may say that I am feeling much better when actually he is not. So the observer must be different from the doctor, and he must not know the research hypothesis nor which group the patient belonged to, and that technique of taking care of measurement bias in subjective outcomes is called as double blinding. Then after this you compare the results here and results here. So the comparison should define both the magnitude of difference and the p-value of difference, either the p-value or the confidence intervals. Because magnitude of difference is the real magnitude that you see in the study population. So much reduction of blood pressure as compared to only this much reduction of blood pressure in treatment group 2. But the p-value tells you that if you repeat the study 100 times, the results would be how much different between the lower and the higher limit of the confidence, 95% confidence intervals or not. So this is the significance. And are the analysis tests for significant appropriate? I mean, should he have done the student t-test? Should he have done the chi-square? So are they appropriate? That is another thing that you can test. Finally, you must comment on ethics, the plan of dissemination, because RCTs are costly ventures and they must go to the last man in the queue. Then are all the approvals there? The ethical committee, the technical committee, the content committee, and is the budget appropriate? So if you can, these are the questions that you comment on when you are evaluating a randomized controlled trial. Now we teach you how to use an Excel sheet for randomly allocating patients or participants to treatment groups. So we open a blank workbook. Here are the participant number or ID of the participants. And let us say this is 1, then we say is equal to sum of this 1, this A2 cell plus 1, sorry, not plus 1, so that we get 2. Then we copy this 2, Control C, and take this down, say let us up to 20. Let us say our numbers are up to 30. And we say Control V. So Control C, and then take this dot from here and go up to 20 or 30. So this is these are your ID numbers of cases. Then here are your groups. The first group is 1, and this 1 you go up to 10. Then the second group is 2. 2 you go up to 20. And the third group is 3. And 3 you go up to 30. So 10, 10 in each group you have to randomly allocate. Then here you write a random number which is equal to rand, bracket open, bracket close, star, and here you write up to 30. And as soon as you press this, there's the random number, and you simply take it up to 30. So all these are random numbers, and now you take this and this combined and go to data and go to sort and sort by column C. And as you say OK, here is your random allocation table. The first patient gets 2, the second 3, 3, 2, and this is how you generate your random allocation table. So this is well, I hope that you have, by repeatedly reviewing this video, you will be able to master the technique of uh, good critical appraisal of a randomized controlled trial submitted for protocol or public publishing, and you will be able to increase the credibility of the randomized controlled trials that we use to affect policy or practice in healthcare.